Example 4. What is the pressure at a point 5 meters from the bottom of a tank of hydrocarbon whose density is 950 kilograms per cubic meter and the height of product in the tank is 10 meters? Dividing the problem into 3 steps. Step 1. Find the relative density from the formula. Relative density equals liquid density divided by 1,000 kilograms per cubic meter. Step 2. Find the height of the liquid above the point in question. Step 3. Find the static pressure from the formula. Static pressure equals relative density times liquid height times G. So here's our question. What is the pressure at a point 5 meters above the bottom of a tank of hydrocarbon whose density is 950 kilograms per cubic meter and the height of product in the tank is 10 meters? Step 1. Find the relative density from the formula. Relative density equals liquid density divided by 1,000 kilograms per cubic meter. Our density was given as 950 kilograms per cubic meter. So dividing 950 kilograms per cubic meter by 1,000 kilograms per cubic meter gives us a relative density of 0.95. Step 2. Find the height of the liquid above the point in question. Total height of liquid in the tank is 10 meters. Height above the bottom of the tank is 5 meters. Height above the point in question is height of liquid in tank minus the height above the bottom of the tank. So the height of the liquid above the point in question is 10 meters minus 5 meters, which equals 5 meters. So we have 5 meters of liquid static pressure acting at the point in question. Step 3. Finding the static pressure from the formula. Static pressure equals relative density times liquid height times G. Relative density is 0.95. We have a height of 5 meters acting on the point in question. So if we plug those numbers into our formula, we get a static pressure at a point 5 meters above the bottom of the tank of 46.6 kPa. The effect of temperature on the static pressure of water. When water increases in temperature, it expands in volume and therefore its density decreases. Because its density decreases, the static pressure caused by a certain height of a column of liquid will also decrease with increased temperature. To accurately calculate static pressure, we therefore need to know the relative density of the liquid. As shown in previous slides, the relative density of water can be calculated from the specific volume at the desired temperature. The specific volume VF of water is found in column 3 of steam table 2. We can then use the formula relative density equals 1 divided by VF. Example 5. What is the static pressure of a 10-meter column of water at 80 degrees C? Dividing the problem into steps. Step 1. Find the relative density of water at 80 degrees C. Use the formula static pressure equals relative density times height of liquid times G. Find the static pressure in kPa. Step 1. Find the relative density of water at 80 degrees C. From steam table 2, at 80 degrees C, the specific volume, or VF, of water is 1.0291. Relative density equals 1 divided by VF. Relative density equals 1 divided by 1.0291. Our relative density is 0.972. Step 2. Using the formula, static pressure equals relative density times height of liquid times G. Find the static pressure in kPa. Our relative density was 0.972. The height of our water column was 10 meters. So static pressure equals 0.972 times 10 meters times 9.81 meters per second squared. So the static pressure at the bottom of a 10-meter column of water at 80 degrees C is 95.35 kPa. We're now going to change pressure in kPa to equivalent head in meters. Head is the height of a column of liquid expressed in meters that would create a given pressure in kPa. When doing pump calculations, we often refer to liquid pressure in terms of head. Head is the height of a column of liquid that would create a given pressure. In the preceding section, we calculated static pressure in kPa from the height of a column of liquid in meters. In this section, we will calculate the height of a column of liquid in meters that would give us a known pressure in kPa. Since our formula for calculating static pressure in kPa from an equivalent liquid head in meters is static pressure equals relative density times G times height, we can find the equivalent head in meters by rearranging our formula and solving for the height. So our formula becomes static head in meters, which is the height of the column of liquid, equals the static pressure in kPa divided by the relative density times G. Example 6. The discharge valve on a pump is closed. A pressure gauge on the suction is open. The source of water is an open tank. If the pump is pumping water at 4 degrees C and the suction pressure gauge reads 90 kPa, how high is the source water above the suction gauge? So we are looking for the height of the column of water at 4 degrees C that'll give us a pressure on the suction side of the pump of 90 kPa, static pressure of 90 kPa. So our formula is our static head in meters, which is the height of the column of water, equals our static pressure in kPa divided by the relative density of the water times G. So our static pressure is 90 kPa. We know because it's water at 4 degrees C, our relative density is 1. So plugging the numbers in the formula, we have 90 kPa divided by 1 times 9.81, which gives us a static head in meters of 9.17. So the height of the water column above the suction of the pump would be 9.17 meters. Example 7. A tank is filled with oil having a density of 750 kilograms per cubic meter and a pressure gauge 1 meter from the bottom shows a reading of 75 kPa. What is the height of liquid in the tank? Dividing the problem into steps. Step 1, we change density to relative density. Step 2, calculate the equivalent static head. Step 3, we find the total height of liquid in the tank. Step 1, change density to relative density. Relative density equals density divided by 1,000 kilograms per cubic meter. Relative density equals 750 kilograms per cubic meter divided by 1,000 kilograms per cubic meter. Relative density equals 0.75. Step 2. Calculate the equivalent static head. Equivalent static head in meters equals the static pressure in kPa divided by the relative density times g. Equivalent static head equals 75 kPa divided by 0.75 times 9.81 meters per second squared. Equivalent static head is 10.19 meters. Step 3. Finding the total height of oil in the tank. Height above the pressure gauge is our static pressure of 10.19 meters. Height below the pressure gauge is given as 1 meter, so the total height of liquid in the tank is 11.19 meters. Example 8. A standby condensate pump has the suction valve open and the discharge valve shut. The pump takes suction from a hot well a certain vertical height above the pump. If the water temperature is 90 degrees C and the pressure of the pump suction is 150 kPa, what height above the pump suction is the water level in the hot well? We'll divide this problem into 2 steps. Step 1, we'll find the relative density of the water at 90 degrees C, and step 2, we'll find the equivalent head. From the diagram, we can see with the discharge valve closed and the suction valve open that the pressure on the suction pressure gauge is due to the static head of the liquid in the suction line. So step 1, we find the relative density of water at 90 degrees C, and from steam table 2, we find VF at 90 degrees C is 1.036. Relative density equals 1 divided by the specific volume, which is 1.036. Relative density is 0.965. Step 2, find the equivalent head. Equivalent head in meters equals the static pressure in kPa divided by the relative density times g. Equivalent head in meters equals 90 kPa divided by 0.965 times 9.81 meters per second squared. So the equivalent head in meters is 9.5. And what that tells us is that the level in the hot well is 9.5 meters above the pump suction.